with a research scientist from JPL, Jet Propulsion Laboratory, Varoujan Gorjian. Thank you so much for being on the podcast.
Oh, happy to be here. Great to meet you.
Yeah, I got your information and we got in touch through a former guest who I'm hoping to have back on soon, Jason Rhodes. When I had Jason Rhodes on, we talked, and I'll throw a link up to our interview. I talked to him about the Euclid Space Mission because Freemasonry is very connected to ideas about geometry, kind of going back to our operative roots. Back when, making sure you had a right angle and knew how to create a right angle, and the pharaoh didn't lop your head off, going back to the days of Egypt. But just how geometry and our understanding of geometry was not only helping us understand the world, but in the case of Euclid, the universe.
Yeah.
But he suggested that I speak with yourself about the Spitzer space mission, which, as you described it to me before we started recording, you're kind of on a greatest hits tour regarding the mission. So if you could spend a few minutes, by all means, what is the Spitzer telescope? Kind of what did it do? What was its purpose? And when you say, you're on a greatest hits tour, what do you mean by that?
Yeah, so in the late 70s, early 80s in the US, there was this move for a program by NASA called the Great Observatories program. So the Great Observatories were meant to be several, and in fact, eventually 4 space telescopes that would overcome the difficulties of doing astronomy from the ground. Now, the Hubble Space Telescope is the most famous version of that, where, again, optical light certainly reaches the ground, and we have ground-based telescopes, but obviously looking through the atmosphere where it wobbles and so on, it doesn't give you the clearest images. But also the Hubble Space Telescope was sensitive to ultraviolet light, which doesn't reach the ground. And so the idea was that, so that was the first one of the great observatories. And then NASA would have 3 more great observatories, each one going to a particular other wavelength region, which is not, detectable or easily detectable from the ground. There was the Compton Gamma Ray Observatory. Again, it's a good thing gamma rays don't reach us to the ground, or if you read comic books, would all be Incredible Hulks, or they're certainly not conducive to life. Similarly, with the Chandra X-ray Observatory, most of our atmosphere absorbs the X-rays, which is great. Not great for astronomy, but great for human and any other kind of life, because you don't want to be just constantly bombarded by X-rays. And the 4th of the great observatories was initially called the Space Infrared Telescope Facility, and which would become renamed the Spitzer Space Telescope. And that one was to work at infrared wavelengths. So these are wavelengths of light that are longer than our eyes can see. And we're usually familiar with infrared light in terms of infrared remotes, like your TV remote and so on. The light that it sends, it communicates with your TV via light, except it's not light your eyes can see. It's a wavelength that it's invisible to you, but it's certainly there. And then and Spitzer actually works even a little bit longer wavelengths than the infrared remotes that we have. And it's very difficult to do infrared astronomy from the ground, not impossible, but one of the difficulties from doing infrared from the ground is the fact that there's water vapor in our atmosphere, which is certainly very good for us in general, but water vapor is very good at absorbing infrared light. And in fact, it's the most common molecule in the air that absorbs infrared and gives us a limited greenhouse effect, which makes the Earth warm enough for us to exist in. Now, we often hear about carbon dioxide as being the infrared absorbing and hence heating and greenhouse gas. It is, and in fact, it's actually, its combination with water vapor is the difficult thing. That is, it absorbs a lot of infrared light as well, and giving us a worse greenhouse effect, which we don't want. But separate from that, all that water vapor in the atmosphere gives us a couple of narrow windows where we can see. and observe the universe. But what we want is to observe at multiple wavelengths, lots of different infrared wavelengths of light. And that was the job of Spitzer. The other thing about infrared light, which people may be familiar with, is that we often hear about infrared cameras where you can see things at night, or they're often called night vision cameras. Night vision cameras can operate in one of two ways. One is they either amplify whatever the ambient light is, whatever light is available. That's just taking the optical light that our eyes would see and just boosting it. The other way is infrared light. That is, everything that's warm, anything that's warm gives off light, and usually things that are just, a little warm to, fairly, and basically they give off light, and that most of that light often is infrared light. And so the advantage of going into space is the fact that our atmosphere actually emits infrared light. So you don't want to look at the universe through this glowing foreground of our own atmosphere. In addition to the fact that a lot of that, the water vapor in the atmosphere also absorbs that infrared light coming from space. So the Spitzer Space Telescope was designed to basically overcome all of those things, first by being above the atmosphere, which makes life a lot easier, so you don't have something absorbing that light. And the other part of it is that if it's warm, it will emit its own infrared light. So you're seeing the light from your own telescope as opposed to the stars and the galaxies and everything else that's out there. So what you want is your telescope to be very cold. And one of the advantages of the Spitzer Space Telescope was by being in space is that you can actually cool it down. And that's the image of it floating behind me. And you see that big shield on one side. That shield actually protects it from the sun and makes it very cool on the tube side, the telescope side. On the other side of that shield is a solar panel, so that's how we get our power. But then no sunlight is allowed to fall onto the telescope itself. In addition to that, we carried liquid helium, which is very, very cold. And so we use that to cool the telescope and the instruments within the telescope. So we could be very cold so that we're not emitting any of the light that we hope to detect from things that are not our telescope, from stars, galaxies, and so on. So that was the genesis of the idea. And then the technology, a lot of technological development had to be done to both have it operate the way it was operating at those cold temperatures, although there have been other infrared space observatories. This was very innovative. But then the other part of it was that, once it was launched in 2003, it was in what's called an Earth trailing orbit, because the Earth itself is warm. So we don't want to be next to a warm thing. If we are, then you have to actually expend more of your liquid helium to keep yourself cold. So we're in what's called an Earth trailing orbit. So we basically had the spacecraft give it just enough of a push so that it started drifting away from the Earth in the same orbit as the Earth is in the sun. That is, we're orbiting the sun at 1 year intervals, just like the Earth is, except we were just slowed down a little bit so that we were just getting further and further separated from the Earth. So we didn't get any heat from the Earth. We had the sun shield blocking the sun from the telescope, and we could go down to nearly 5 degrees Kelvin to basically be very cold. So then anything that was warmer than that in the universe, we could detect the light and observe it.
That's something you said got me thinking. I think it's interesting. I never thought of it in this way before. You kind of talked about how there was the initial desire or initial question about researching infrared light, and then you said you had to have the technological innovations catch up to the initial idea to make it possible, such as whether it be the shield or the liquid helium and the cooling system. That's with NASA, with JPL, how often is it that the idea comes first and then that forces innovations and technological advancements to make the idea possible, or does it ever work the other way, which is kind of a new technology develops and you recognize it can be used for applications that were initially thought of or considered?
Great question, and it actually works both ways. We usually have ideas and there's technological development that spurs basically the technological development. We want to, particularly in the infrared, the idea was we want to look at things that tend to be much cooler than our sun. So our sun is very hot, therefore it also emits in the optical as well as in infrared light. But things that are cooler tend to be just mostly in infrared light. And the idea was that we needed to get better and better detectors. And so that was pushing the development of that technology because we wanted to function better at infrared wavelengths. In the 60s, actually, the technology came from the military because they were doing heat-seeking missiles, which again, something is warm, it's emitting infrared light. And so the initial development for electronic infrared detectors was spurred on by the military, but then that technology was then passed on to astronomy. But then the military's needs were very different than ours. We work on we don't need to expose, instantaneously. It's not very fast situations. We tend to, to expose for a long time, but we need higher sensitivity, lower noise in our detectors. And so for many years they worked, so the development of infrared detectors was being driven by what we wanted to do in astronomy. Simultaneously, though, we often get, developments that that come to fruition, but from other reasons. And in this case, again, the military had developed the infrared detector, and we literally it was 1 pixel in the 60s, and they could take that 1 pixel that they'd gotten from the military and then basically just march it across the sky to get an infrared image created. So I'm not saying it was like, right now we're used to 1 megapixel, which is multiple megapixels. That's 1,000 by 1,000 array of pixels. There we had just 1. So that was the technology that came to be, and it was used for astronomy, and its use showed that improving it would be giving us a lot of dividends in astronomical observations. So then that spurred the development of infrared detectors to do astronomy. Same with the cryogenic systems, that is the systems that kept the telescope cold. It's been a feedback kind of thing. It was developed for various other reasons, and then that was applied to situations that were for astronomy, and then we could do better astronomy, which meant we needed different kinds of cryogenic systems. So it's always a feedback. And so a good chunk of a JPL is, specifically as an example, is there's a lot of engineers at JPL who are working on developing the technology that will help space exploration. And oftentimes it's driven by something very specific. We need to achieve this. Therefore, they're working on the technology to allow that particular science to happen. But oftentimes we get situations where, things have been developed elsewhere that somebody says, hey, what if we use that for astronomy? And so people go, hey, well, let's take that and use it. And then if it becomes useful, then people go and use that technology. But we're always on the lookout for something new, but at the same time, we're not just waiting for that new thing. Is that there's efforts being made constantly to either create or improve the technology so that we can do astronomy or do better astronomy.
Does it ever work the other way, in the sense of, a piece of technology is developed either related to space exploration or otherwise defense, whatever it is, and then somebody recognizes a use for that technology that perhaps wasn't initially envisioned, or it causes people to reevaluate, as opposed to, I know, the one way, as you described, right, is there's a specific need, and then you ask an engineer or the engineers, we need to do X, can you develop the technology? Has there ever been the opposite way as well, where technology is perhaps developed for one purpose, but you realize it can be used for something else very well?
Well, we're actually using it right now, in fact, almost all of us. So the particular kind of detector that sits in most, if not all, cell phone cameras is called the CMOS. That was developed at JPL. Why? Well, what they needed when you have a space mission is a camera that is small, that is light, that uses very little power, because all of those things are at a premium when you're in a space mission. You can't be something that's too heavy. You can say, oh, it's just the camera can be heavy. Well, then everybody can say that, and suddenly your spacecraft is way too heavy to launch, or way too heavy to launch economically. That is, we don't have tons of money all the time to be, every ounce counts, every gram counts. And so that was developed with the express purpose of, let's not have our cameras be too heavy or use too much power. And then somebody said, these new cell phone things, they don't have a lot of power, they don't have a lot of room, and you don't want them to be too heavy. What if we put a camera in there? What kind of camera, what kind of detector can you use? And that was, that was from the space program. And we usually call these things spin-offs. That is, it was spun off of something that was, again, entirely motivated and driven by something very specific to space exploration.
That brings to mind for myself kind of an interesting connection or correlation in some Masonic teachings that we have. There's this one line when you're getting your degrees, which I've always really liked. The basic premise of it is, as you increase in knowledge, you kind of increase in social utility. You can benefit. The more you know, the more knowledge you have, the more beneficial you can be to the world around you. And that's something I really think we can sometimes lose track of when it comes to matters of quote unquote pure research. So when it's, exploring the galaxy, exploring other planets, there can be some people have questions about, like, what is the practical value of X or Y. I guess my thing is you never know for sure. The more knowledge you have, the more likely you are to find practical benefits down the line. The quote, what was the quote about the electron? I can't remember what it was. I think somebody, when they discovered the electron, I read some book, said, like, it'll never be useful for anything. It's just a cool thing we found.
Well, it was very much like that. I don't know if it was specifically for the electron. I can't remember, but a little over 100 years ago, the hottest field in physics was this new idea of quantum mechanics. What is the physics of the very small, which includes the electron, the proton, understanding the nucleus of the atom, the fact that it had a nucleus and, which had positive charges with the protons and the neutrons in there, and then the electrons were, orbiting and floating around. And all of this stuff at that time was entirely, I wouldn't say purely theoretical, because there were experiments to verify the theories as well, but there was nobody who was doing it with the idea that this has a practical application. Fast forward to today, everything we do is based on our understanding of quantum mechanics. Everything that has these solid state devices, these very, very tiny, all the stuff that's crammed into the chip, in your computer you use, or in the phone you use, or in the DVD player you have, and all of this stuff is entirely a consequence of our understanding of quantum mechanics. Now, again, nobody was thinking that this is going to have some sort of a practical application. And you don't know how long it's going to take, but it's a very reasonable question, and I don't bristle at this at all. That some people say, oh, if you're doing pure science, you shouldn't be questioned because it's so noble. No. I mean, there's nobility, there's value in knowing things. If you ever watched old MGM movies, the Metro-Goldwyn-Mayer movies, its title was, "Art for Art's Sake," was written in Latin. And there's knowledge for knowledge's sake. That is, you gain knowledge because knowing more helps you in general understanding. Now, there is a real place for that, I think, in research. But at the same time, we don't want to detach ourselves from the world. There's definitely, then you can do applied research, and then eventually then it just becomes what we would say, it goes into the realm of engineering. So how do you implement what you know at this point? And so fundamentally, in terms of how is it useful, We don't know how it will be useful, just like the people who created quantum mechanics had no idea how it would be useful. But as you were saying, exactly, as the knowledge increases, the connections become more, and at some point, suddenly it's not only just simply useful, or it's nice, it becomes indispensable. That is, our current world would not be possible. This conversation we're having would not be possible had it not been for the work that many great physicists, Einstein, Heisenberg, Planck, Bohr, the very famous physics people, but not one of them could have possibly envisioned that what they were working on would have any consequence like this. And similarly, in astronomy, that's part of it as well. That we don't know how this will be applicable to our lives in the future. Having said all of that, I will say, something for knowledge for the sake of knowledge, or art for the sake of art. There is inherent value, I think, in that, beyond whether it has some, something that is a practical return in the future. And I think the way to look at that is, what is the value of the Mona Lisa? Now, yes, it has a dollar value associated with it. That's not what I'm asking. I'm saying, what if somehow, if we waved a wand and magically all the Mona Lisa's copies and the original went away from, did not exist? Or any of the great works of art, or sculptures, or even architecture, the pyramids, let's say, boom, gone. Is there, if the pyramids aren't there in Egypt, yes, their tourist value is no longer there. But I would say there's something more, that there's value in those great creations. And I think if we waved a wand and went away, there's no practical use of the pyramid at this point. There's no practical use of the Mona Lisa. But it is, I would argue, and people may argue against it, but I would argue that the world will have lost value if those things did not exist. And I would argue the same for astronomy, is that knowledge, for the sake of knowledge, has its own inherent value.
Yeah, that is definitely, I think, a Masonic teaching is the idea of knowledge as having an inherent value and being a benefit to to oneself and to one's ability to exist in the world. That the more knowledge you have, the better citizen you're going to be, regardless of the quote unquote practical application of any of these things in your life. I'm not a builder, so I've never needed to make a right angle. But it's still good to know, a squared plus b squared equals c squared. I feel like just having that knowledge ultimately makes me more useful to society as a whole, and of better utility to it. So lifelong learning, and one of the reasons I'm so honored to have scientists and people from JPL on this podcast is that Masonic idea of constant learning and lifelong seeking of knowledge, so to speak. Speaking of seeking of knowledge, because I'm a dummy and I don't know very much, I guess going back to the Spitzer telescope, why is it important to study infrared in particular, or even more generally the four, because there were four telescopes, each studying a different type of light, whether it be the visible spectrum or infrared. I guess, why is it important to differentiate and focus on infrared as well as visible, as well as UV, X-ray, all the types of light spectrum?
So that's a great question. And it's one of those things, so there's sort of a much more direct practical version of it that I can give you, is that, yes, I mean, from the gamma rays to the infrared, that's a long range of wavelengths of light, but what if we just talk about the wavelengths of light that our eyes can see? How much less would you know about the world if you did not see all the colors? And some people can answer that if they're colorblind. That's the thing, is that we have this range of colors in the rainbow from indigo to red. But if we had less of those, or you couldn't see, if you only saw the reds and never saw the blues, the greens, and the purples, you would know less about the world around you in one form or another. So there's that part of it. But what's the reason you want to follow all of those kinds of wavelengths is because different physical processes, different things that are happening generate different wavelengths of light. And the most common way that is how hot something is. The hotter something is, the shorter the wavelength it emits. So if something is, now we're sort of used to this in our own lives, what we may not, pay not much attention to it is, if you put, an iron into a fire and it starts glowing red, we think, oh my God, that's very hot. But if you really look in a furnace, then it gets orange and may have even eventually hot enough to be bluish. Or if you see an arc welder, which we associate with something that's very hot, the welding is done and you see it, it's incredibly blue. And of course, the guy has to have the big mask with the thing covering the eyes. But that's because it's very hot, and very hot things emit very blue light or shorter wavelength light. And in fact, in the universe, things get so hot in cases where they start emitting ultraviolet light and then X-ray light and even gamma ray light. Although gamma ray light and some of X-ray light, there's different processes that can generate that. It's not just simply hot in terms of thermal heat. And then there's a lot of things that are very cool. Their temperature isn't very hot, so they're not emitting very much light. And that's one of the things that the Spitzer Space Telescope was designed to study, was these things called brown dwarfs. These are things that are larger than planets, but tend to be smaller or less massive than stars. So they don't have that intense fusion, the conversion of hydrogen into helium at their cores, which generates a lot of energy, which makes stars glow. And our sun does a fairly good job of it. And you can look out and it's giving mostly whitish light because it's a combination of lots of different wavelengths. And if our star had more mass and it had a lot more energy at the core, it would generate a lot more energy because that mass would be forcing a lot more fusion to be happening at its core. That would be, our star would be blue. And if it was less massive, it would be cooler, it would be red. But brown dwarfs, for example, are so cool that they don't emit almost any light in the optical. They're emitting most of their light in the infrared. So to study that was one of the goals of the Spitzer Space Telescope. The other advantage of multiple wavelengths of light is that certain things block certain wavelengths of light. As I was mentioning, the water vapor in our atmosphere blocks a lot of infrared light. But in the rest of the universe, there's a lot of different things that block, for example, optical light. There's a lot of dust in the universe, that dust blocks a lot of the optical light that's coming to us. And oftentimes when stars are forming, they're enshrouded in dust. So if you want to study stars forming, it's very hard to do it in the optical because you can't see through that dust. But infrared light is actually very good at penetrating the dust. So Spitzer could look at places where we couldn't look with the Hubble or other optical ground-based telescopes. And so we could study what was going on at that, in the cores of these clouds where young stars were forming. So fundamentally, it's the different wavelengths of light are really giving you, each one is like a different window in the universe. And there are certain things that block infrared light that don't block other wavelengths of light, like I said, like water vapor. And then it goes on and on for different wavelengths. So each wavelength in and of itself has an advantage. And then when you put them all together, then it's like putting all the colors of the rainbow together as an analogy to the optical light. You get a multicolor, full spectrum view of something. And so you can understand it a lot better. And so that's one of the key reasons why the great observatories were done initially. And again, those aren't the only wavelengths of light. It goes even longer wavelengths than radio wavelengths, but the atmosphere doesn't really block radio wavelengths, so we can do that from the ground.
Do you ever think it will be possible? This is kind of more maybe a metaphysical type of question. Do you ever think it'll be possible through the use of technology or maybe some type like artificial intelligence to get the quote unquote full picture of the universe, in the sense that, for the first, I don't know how long humans have been around, say 200,000 years from hominids, right? We were only really aware of light in the visible spectrum that we could see. And then, through the use of technology, we recognized there's actually light waves that our senses on their own aren't able to detect. So, for so long, we only had a limited view of just light, let alone the physical reality, quote unquote. And then we recognized through technology, there's in this case infrared light, there's X-rays, there's gamma rays, there's radio waves, and all of these pieces of technology take what our limited senses and then expand them so we can see a more and more fulsome picture of the universe, just like the Spitzer telescope does. Do you ever think there'll be a point at which technology will become such that we are able to get the full quote unquote picture of what the universe is, a theory of everything maybe, or I guess, how would you test that though? Because you could always assume everything until the next thing comes along.
That's a good question. I think it's certainly a difficult thing to really project forward, but that is really what our jobs are. Although, I mean, we all specialize in different aspects of the, what specific areas of astronomy, since the universe is big and everybody studies different parts of it, and the different bits and pieces that go into it. But the reality of it is, that is what we would like to ultimately have, is a coherent picture supported by evidence of how the universe started, how it evolved, and how it got to the point where we are today. And we've certainly gotten, we're a lot further along on that, than we were before. I mean, people, even just barely 100 years ago, people didn't even understand that, the universe, what they called the universe, wasn't, all simply the stars and that people could see. They didn't understand this concept of galaxies, which are, they used to call them island universes, but they weren't, they thought there were these things which were, nearby, as opposed to hundreds of billions of stars very, very far away. And that the fact that there were hundreds of billions of galaxies out there. We've come a long way, and the idea that we are living in a universe that is evolving, that did have a point of origin at this point in terms of time, that there's a beginning to the universe. And it's been a great success of astronomy, but there are very, very many aspects which we have not figured out. We certainly don't know what most of the universe is made out of. I mean, we initially thought, wow, atoms, great, we understand atoms, that's what most of the universe is made of. And certainly what most of the universe that emits light or interacts with light is made out of the kinds of atoms that we're familiar with. But there seems to be some kind of matter out there, labeled dark matter, and that does not seem to interact with light. It's not simply that it's a color black. It's that, having gone through all of these wavelengths, we know that it exists based on its gravity, because galaxies, if you look at how they're rotating, all the stars are rotating, they're moving much faster than you would expect them to. You would expect them to be flying apart, and they're not. So there's a lot yet for us to figure out. And what I would say is that, for astronomers, that's job security. But at the same time, ultimately, that's what we want. But could we, how well we can understand it is really partly dependent on the instruments that we have. And we're getting better instruments as time goes on, and we're honing in on what kind of instruments we need to have. We've recently even developed what's called gravitational wave detectors. This was something that was theorized under Einstein's theory of general relativity, which describes gravity, and that as things move, and certainly as things are more massive, things like black holes, which are lots of mass concentrated in a little volume, they generate these ripples, these waves in what's called space-time. But basically, that's not a light wave. It's a fundamental disturbance in the fabric of space. And now we've been able to detect that, and that won the Nobel Prize a couple of years ago. So now, again, we're increasing our tools to increase our understanding of how the universe works, and that's what we want. Ultimately, we want a good, coherent story of how the universe came to be and how it functions. But I think we're a long way from that at this point.
You used the word coherence a couple of times.
Mhm.
I guess could you expand on that? What would make a coherent theory or coherent picture of the universe versus an incoherent one? Like, is that connected to kind of the struggle between, connecting general relativity with quantum mechanics, or I guess what do you mean by a coherent picture?
Oh, it's a good question. No, you brought up exactly the example I'm saying, is that we have these two aspects of physics, general relativity and quantum mechanics. Quantum mechanics describing all of the physics that happens on the very smallest scales, general relativity describing things and on the things that happen on the biggest scales. But there's an intersection, which particularly happens at black holes, where you have a lot of mass concentrated in a little volume. So since it's a little volume, quantum mechanics should be ruling that. But because there's so much mass, gravity has that. And that's incoherent. They are not really doing a good job of predicting what will happen. So that tells us that we have a problem in our understanding of nature. That's what I meant by coherent, because there's these two different things, two different theories. Each one in its realm works very well, but when you bring them together, they're not really matching up very well. And so that's, I think, the key area that there's a great deal that can be learned is how do we have a single physical description of how matter interacts, both through the fundamental forces of electromagnetism, and there's the weak force and the strong force, which happens on operates on the atomic scale, and gravity, which is a very, very weak force, which under quantum mechanics, it should be somehow related to the other forces, but general relativity actually completely abandons the quantum mechanical idea where everything is particles. And it's this idea of waves going through, or the fabric of space being altered. So that's the main thing I meant by coherence, is that you can't have your description for how one part of the universe works not match up with your description of how the other part works.
I wonder, is that in desire for coherence, or I guess is that a statement of desire based on kind of our evolution, like human beings being evolved as pattern seeking beings, right? We have a desire to, certainly our survival, especially in the early days, was based on being able to recognize and to see patterns in the world around us, and then apply those to our lives, whether it be, following animals to hunt, or seasons for farming and agriculture. So our desire for coherence, or the use of kind of the struggle people have with, say, quantum mechanics versus general relativity. Do you think that actually, could it be that doesn't so much reflect that's not a problem in nature so much as just our brains are wired to desire coherence in life? Or do you think that when you see incoherence, it actually represents a lack of understanding on our part and something that can be solved?
Uh, I would say it's the latter. I mean, I completely concede. I mean, humans are pattern-seeking animals, and so we tend to want to see things, and we want to see things in a particular way, or we're hardwired to see things in certain patterns. But in this case, and in the case of, I think, our general understanding of the universe, is that whenever you get these incoherences, then there's something wrong. Or there's something new to be found. And I'll give you an example, again, from this happened in both physics, the intersection of physics and astronomy. So once the initial understanding of light came to be, people thought that started understanding light as a wave, because you could have like little slits and the light would interfere with itself the same way if you have like two little holes and water is going through, you have the ripples, and the ripples can positively interact or negatively interact, so you get extra high peaks or extra low valleys. And so people said, oh, light is a wave. And the understanding was that, well, if it's a wave, there needs to be a medium through which the wave travels. Okay, something needs to be waving for a wave to go. The water needs to be, or if I'm sound waves, the air needs to be vibrating in some fashion for the wave to travel. And somebody said, well, okay, well, how does the light get from the sun to the earth? Well, under that understanding, there needed to be a medium which filled the space between the sun and the earth for the light to wave that medium for it to get to us. And so people called it the luminiferous ether, that there was this ether. But then somebody else said, but wait, if the earth is orbiting the sun and it's going through this ether, that's going to have viscosity, which is going to slow the earth down, and we're just going to spiral into the sun. And they said, well, we're not spiraling into the sun. So this luminiferous ether, we found something new about it, about the luminiferous ether. The ether has zero viscosity. Okay. But then people started measuring the speed of light, and it was like, oh my God, the speed of light is very fast. And for a wave to travel through something, the speed of the wave depends on the stiffness of the material. And so since light is traveling so fast, this material should be incredibly stiff to have light wave through it very quickly. So suddenly we have the ether, which has to be zero viscosity and incredibly stiff to match the observations that we have. And people started looking for it, and they couldn't find this material that this happened. So it wasn't until later when people understood that light, even though it behaves like a wave, you can see it as particles moving out. So it doesn't need a medium if you look at it that way. But also there's another way of looking at it, even as a wave. It is an electric wave, which causes a magnetic field, which causes an electricity and magnetism are connected. So it doesn't need a medium. But the fact that they had predicted that this ether should exist based on their understanding of how light worked as a wave, and the fact that they couldn't find the ether, that there's some incredible experiments done to find this ether. It was the most important of it, which was called the Michaelson-Morley experiment. People can look it up. But fundamentally, again, it was that incongruence. It wasn't simply that we were looking for something to be consistent, but the experiments were saying one thing while the theory was saying something else. So one of them had to give. And either the experiment was not done properly or correctly, or the theory was not correct. And the experimenters got better and better at it, and it just would not yield in that sense. So then the theory had to change, and it did. And it was partly what we got us quantum mechanics, and that in our understanding of quantum mechanics, everything are particles that travel, and the particle of light is the photon. But it is one of those things. As soon as you have this incongruence, that there's something that's not matching up, something has to give. And I think that's what we would really like, is so that you don't have these inconsistencies or conflicts or predictions which the experiments aren't finding. So that I think is really the exciting part of science. As a scientist, it's great when you do an experiment and it verifies your theory. It's very satisfying. But more often than that, I would say it's even more exciting, maybe not as satisfying, it's more disturbing, is like, and you get an experiment or you have an observation and you go, what's that? Or that's not supposed to be there, or that's not supposed to be doing that. And then that is an opportunity to learn something new about the universe.
Yeah, and that's the fascinating thing about, I think, people. I have an interview coming up with some neuroscientists. One thing I talk about a lot, and this goes to kind of Freemasons' operative roots as well as our buildings, talking about the connection between neuroscience and architecture. And one thing we talk about is, or we will be talking about is, and you see this in Freemasonry, when we see, for example, a right angle or certain patterns in architecture, going back to the ancient Greeks, like the golden ratio, even if we can't, we don't have the training or the knowledge, so we can't physically or we can't verbally express why, I guess there's been experiments and stuff that have shown that on the perception level from the brain, it just prefers seeing things that fall into these golden ratios, right angles, things like that. It seems that human beings, by our nature, are very inquisitive and have a desire to find coherence, whether it be in scientific theories or in architecture or whatever it may be. And so I think that's probably ultimately one of the reasons that, human beings have been so successful through the years is we'll investigate something if it doesn't quite seem to fit. Because it's in our nature to want to figure out why something is not fitting together properly and then see if there's a way that we can explain it or make it fit correctly. Right,
Oh, yeah, I agree. Yeah, I mean, it is. I mean, it's not even a matter of agreement. I think that is like human nature. We do have a sense of that certain things have to be in a certain way, and I think. But what I would say is that that shouldn't be sort of conflated with the idea that some people do want to make things fit, even if they're not fitting, and just sort of pretend that that's the good thing about science is done. By how could I describe this?
I guess that would be one of the benefits of, for example, JPL, NASA, of the scientific method is, it provides some type of framework and rigorous training. So you can differentiate between theories or ideas or statements that are based purely on a desire to make something fit versus an actual scientific rigorous method where you recognize, you perform experimentation and you recognize that it's not enough that something sound good or sound reasonable. It needs to be tested and observed. And you need to be very rigorous so that you're not allowing your own human nature bias for order to creep into your experiments.
Yeah. So what I will say is that that's the ultimate goal and that's the ideal. That rarely is how it works because human biases your experiments, biases those kinds of things. But the beauty of the scientific method isn't simply that it's just each individual trying to apply it, is that there are others who are also trying to apply it with their own biases. So in that conflict of trying to, and again, I'm not saying that people try to be biased, but we are oftentimes just are unable to see the bias within ourselves and even within a certain idea that has taken hold within a particular scientific branch that will stay a long time. But what's interesting about science is that the idea was that somebody had proposed the idea with that science can only advance once the older people die and so take their prejudices away and sort of these new ideas. But it's not quite like that. So we do have our prejudices. We're human beings. That's the way it works. But the scientific process, by pitting these ideas against each other, that the experimentation has to constantly, be something that supports whatever point of view that you're doing, basically makes it so that there have been times, and astronomy is a very good example, although there was a lot of people who did not think the universe had, a particular age. They thought the universe was infinite. Once various pieces of evidence came to be, the expansion of the universe, and then the remnant heat from that initial very hot expansion called the cosmic microwave background, you didn't need to wait for all the old astronomers who believed the universe was infinitely old to die for the new idea to take hold. It switched very quickly. And this is what there's a philosopher of science, I believe his name is Kuhn, who said it's the paradigm shift, that there's a quick change, relatively quick change from one point of view to another. But what I was just saying is that I don't think, and I've seen this, it's like scientists aren't necessarily trying to be biased, but we can't sort of divorce ourselves from that, because as human beings, you're always going to have a certain point of view. You're always going to have, and it's good because you want to defend that certain point of view and look at it this way, look at it that way, to keep that point of view going, except you have to let it go at some point where the experiments just don't support that anymore. And that, I think, is the value of the scientific process, that at some point, the experiments don't support your position and you have to accept what the reality is. And there's been a few scientists who never accepted that. There's a few people who never quite accepted the Big Bang Theory again, not that it's right, but that the evidence is overwhelmingly on that front. And then some people were like, no, no, the universe is still infinitely old. This is all different kinds of explanations. But again, that's, like I said, it's reflecting human nature, and we're humans and just like everybody else. But hopefully, and what we've seen is the scientific process over time does matter and does separate the good from the bad over time.
Yeah, whether it be science or I've heard the expression, masonry advances one funeral at a time. The basic idea, right, is that, but as you say, that's not the hope. Uh, right, these paradigm shifts don't have to come when the old guard all passes away, right? Paradigm shifts can come if there's evidence or something persuasive to kind of force the issue.
Mhm.
One thing that I really found fascinating when I was talking to Jason Rhodes, now I'll throw a picture up on the screen. In our lodge room here at the Windsor Masonic Temple, we have a picture of the Pythagorean theorem of Euclid's. I should know this. Euclid's 42nd problem, if I do recall, right? 3, 4, 5, and that's something that was discovered or proved over 2,000 years ago. Over 4,000 years ago, really, or not, whatever, over 2,000 years ago. But yet, you have a spaceship being launched up, or a telescope being built, getting ready to launch into the solar system. That's named after the person who proved this. That's using these very simple geometric principles that have been known for thousands of years to understand, the furthest reaches of our universe and how our universe works. I guess for the Spitzer mission, for your work, I guess, how do you find it, like, these, it just amazes me how you have these simple, quote unquote, simple ideas, things that have been known for thousands of years that we're still using in our ability to understand the world and the universe.
Uh, it certainly is one of those things that is, I guess, satisfying is the way to me to say it. That is that it's not that things aren't complicated, or it's not that things can't get complicated. But what is truly amazing about the universe, and Einstein has famously been quoted, gave a quote, is that something along the lines of, what the most amazing thing about the most inexplicable thing about the universe is that it's understandable, or something along those lines. And it is. That's the thing, is that we are using a lot of basic concepts, some of them which date back thousands of years, to understand something that's much, much bigger than us, much more complicated than we could have ever imagined in many ways. And it may yet become so much more complicated that, some of these, that we have no idea of how complicated it can get. But there's still some very basic ideas underpinning all of this stuff. And I think that's the thing that has always attracted me to astronomy and just science in general, is that not all of the concepts, there's a lot of concepts that are very difficult and take many, layers upon layers and upon layers to understand. But there are some which you actually, it's not that complicated. We thought they were, but then you can actually break it down into some component parts, and those component parts are relatively simple to understand, and you put them together, and that helps us understand it. And I think that's what often gets lost in teaching science as a series of facts in most schools, is that science is not the ultimate, it's not a body of knowledge. It is a way of doing things. And the way of doing things is you take what you have. You have to take these very fundamental concepts of mathematics and the basics of physics and chemistry, and now we're going to astrobiology. So biology, you put those things together, and that's, it gives us all of the things that we see in the universe. And that's one of the things that really I find both, like I said, satisfying, but also fascinating, is the idea that you have you learn a certain set of things, but you can put them together in a way to understand the universe. In particular, I mean, the best example of this is chemistry. I mean, again, people don't may not know that the basics of chemistry, the periodic table, it wasn't until, people knew various different kinds of elements existed, but the idea of periodic table, how that, relations between each of those elements as they get heavy along those lines. But that is, the universe is not made up of anything other than that. It's not made we don't need new elements every day as we're observing to understand, the universe. It is those very basic components of the periodic table that, if you look at it, that's what the universe is made out of.
Yeah, I think I heard Neil deGrasse Tyson. So many talk about, what's in the stars is in us. It's
Yeah.
not a lot of things, but from relatively simple or small things, you can create some very complex and beautiful systems.
Yeah, and by the way, that's not to say that there weren't certain things that weren't discovered in space first. In fact, helium, named after the god of the sun, Helios, was first discovered when people were taking spectra of the sun. Spectrum is when you split the light through a prism, and people thought, oh my God, this is something is on the sun that wasn't on the Earth, and they were right in that case. And eventually, we found helium on the Earth as well. So there was an element that was common on the Earth that was in space. But then there are other elements. In particular, there was one called Nebulium, which was in these, particularly where either stars were forming or stars had died, and people would look at those. And that's one of the things that Spitzer studied, particularly young star forming regions, as well as what are called supernova remnants. And so people would look at those, and they saw, the pattern that they saw were not familiar for anything on the periodic table. So they thought it was an entirely new element like helium. What it ended up being was that, no, it was just the physical conditions, that this was a very thin gas, that collisions amongst the atoms were not very common, and that you would get those. And in fact, we were able to reproduce those from with gas on Earth, particularly like it was varieties of oxygen or nitrogen and so on. But it was just interesting that, again, it is, other than sort of this odd case of helium, really the universe is the stuff that we see in the periodic table. Most of the period isn't as common as a few of them. So, and the ones that are the most common things of those, hydrogen and helium, are the things that were mostly created. Hydrogen certainly, and most of helium that was created pretty much at the beginning of the universe, but most of the other elements were forged in stars through fusion. And so this is what Neil deGrasse Tyson talks about, the universe is in us. Carl Sagan said, we are star stuff. And that's what he's talking about, is that these heavier elements, particularly the ones that are most common, carbon, nitrogen, oxygen, are really from the fusion furnaces of stars. But again, these are fundamental basic building blocks, and the universe is made out of these. And it's always, and the mysteries that we work on is like, how do you take the basic laws of physics that we know? How do you take the basic elements from chemistry that we know, and you put them together, and we see what we see when we look out into the universe?
So you are, this is a bit like a rock star. You're on your greatest hits tour for the Spitzer telescope. Because I understand that it completed its mission in last year, 2020. I always wondered what happened. Is it still just floating around up there after it completes its mission? Does it fall back down to Earth? But also, what are some of the greatest hits of the telescope in its 12-year mission? Some things that it discovered that you're particularly proud of, or the team is proud of, and what's it up to right now? Is it still just up there circling us all?
Yeah, so I have 17-year mission, actually. So,
17, that's 2020, that's right.
Yeah, that's a little bit less than that, 16 and change. But so yeah, so first of all, if you remember, I mentioned, so Spitzer is actually in an Earth trailing orbit. So it's going to remain in orbit around the sun like the Earth is orbiting around the sun. And in fact, because it's trailing us, it will eventually meet the Earth in about 60 years on the other side, as that it'll slowly approach the Earth from the other side. again, it's right now, it's been shut down. It's not listening for signals or anything. And part of it was, so there is sort of two major phases to the mission. There was what we called the cold mission, where we had liquid helium on board. The liquid helium was evaporating, but as the process of the evaporation was, and it was keeping the instruments cold. But once we lost the liquid helium, many of our instruments no longer functioned, and we warmed up. But by warming up, we went from 5 degrees Kelvin to 30 degrees Kelvin, which is, again, remember, the Kelvin scale is minus 273 degrees centigrade. So it's still very cold, and we were able to continue for many years with those fewer instruments to be able to study the universe. But starting off, I think, in terms of, for all intents and purposes, it's basically space junk at this point. But the main thing is the successes were just enormous. And even though the telescope itself is no longer functioning, the huge amount of data that we have, we're still sifting through it. So the discoveries will be coming through for many, many years to come from the archive of data that it's created. But sort of beginning, I think, really nearby in terms of its sort of greatest hits, when it was Spitzer discovered the largest ring of Saturn. And you would think, well, if it's the biggest ring of Saturn, isn't that like the easiest one to find? Why did we miss this largest ring of Saturn for hundreds of years? And it turns out that this very, very large ring of Saturn is actually very tenuous, so it doesn't scatter optical light very much, but it's warm enough that it was emitting in the infrared. So looking at this in the infrared, we were able to see this incredibly large ring of Saturn. And also, we were able to study comets in our solar system, and there was a mission out of JPL called Deep Impact, where a projectile was launched to hit a comet, and there was a spacecraft that was monitoring that, but there were all these telescopes that were monitoring. The idea was that the surface of the comet, as it comes close to the sun and further away over the millennia that it's going around, gets essentially weathered. That is, it's interacting with the warmth of the sun, and that's what makes it evaporate. That's what gives the comet the big tail. But there's chemistry. You're putting energy on the surface, and therefore you've got chemistry going on the surface. So it's not the pristine material from which it had formed, but inside the comet, this ice within it is much more pristine. And so that's what was supposed to bring it out. And so we were able to observe that, particularly with Spitzer. And Spitzer also observes other stars and was able to see similar chemistry akin to the comet that we had the Deep Impact mission on. And so we could see that it looks like other solar systems have similar chemistry to ours. It was able to observe young star forming regions, so we were able to peer at these baby stars. And then in particular, the area that I work on, which is these supermassive black holes at the centers of galaxies, oftentimes they're enshrouded by dust. And so Spitzer was able to peer through that dust to study more of these. And the emission of the black hole, it has no emission, but as material falls into the black hole, it heats up and emits at lots of different wavelengths. But if it's at the centers of some galaxies, it's pretty dusty, so we could look through the dust and study those as well. And then you get further and further out. We studied star formation not only in our galaxy, but in other galaxies. And then the most interesting bit, we were able to see, because of our great sensitivity, we were able to see these very, very early galaxies, which was a bit of a surprise. Not that they existed, we always knew that they would, but in the infrared and in combination with other great observatories like the Hubble Space Telescope and the Chandra X-ray Observatory, but we were able to particularly get whether there was activity going on. For example, that there was a supermassive black hole early on, so there's excess light coming out of it that you would not expect based on the total stellar population. And these are called active galactic nuclei. Or when you combine Hubble and Spitzer in particular, we could get sort of a sense of the age of the stars. And we saw that there are some very young galaxies that had sort of oldish stars. So they were able to form stars very quickly in the early universe, and that was a surprise. And so that was one of the key things that we were able to do looking at these longer wavelengths, in particular because as the universe is expanding, that light is being stretched out, and this is called the cosmological redshift. So things are being shifted towards the longer wavelengths of light. That's what we call it, a redshift. And so that was another key thing, that we were able to find these very early galaxies looking very far away. And the further away you look with a telescope, the earlier you're looking back into the history of the universe, simply because the light from that location now is not young anymore, but the light that was emitted when it was young took it this long to get to us. So instantaneously, it's not young, but we are seeing it as it was because it took so long for the light to get here. And in the infrared, we could get a good sense of how old the stars were in those early galaxies. And it looks like star formation in galaxies started very early on after the Big Bang. So these were at least, just a few of the great discoveries that were made, particularly, and I'll bring it back to the area that I worked in, is in active galactic nuclei. They're particularly, as material falls into the black hole, it heats up and it hits up its environment. So looking at it in the infrared actually is a very efficient way of picking out these active galactic nuclei. So we had huge surveys that were found very, very large numbers of these supermassive black holes at the centers of galaxies that have material falling into them. So this is just a few of the highlights of the Spitzer Space Telescope. I would encourage people to go online and do a search on the Spitzer science, and I don't want to sort of diminish any one science, but I will end with, I think, one of the things that was, again, the most unexpected in terms of what Spitzer was able to do, and that is shortly, a few years before the launch of Spitzer, the first planets around other stars were detected. And oftentimes, one of the ways that you detect these planets around other stars is what's called the eclipse method or the transit method. So if you have a star and it has a planet, and you're the viewer is the telescope, if that planet passes in front of the star, there's a minuscule dimming of the star because the planet is now blocking some of that light. So using that technique, we've been able to find a lot of planets around other stars. Now notice, that's only for a special case, that it has to be properly aligned. That is, if the planet is in orbit, but the plane of that solar system is different, so it's going like this, you're never going to get an eclipse. It has to be, like this. So, but what's interesting about what we were able to do with Spitzer was, so this is what's called the eclipse, but then there's what's called a secondary eclipse. And that is, the planet goes behind the star. Now, the planet itself is not generating, is not doing fusion to generate light, but it is warm. And that warmth is generating its own infrared light because it's not very hot, but it's warm enough. So the star is emitting infrared light, the planet is emitting infrared light. And when the planet goes behind the star, so if you image them, again, you can't separate the planet out from the star, it's just a dot on your picture. But what's happening is that when the planet is next to the star, you're getting starlight plus planet light. And when the planet is behind the star, you're only getting starlight. And if you take two images, or you follow it over time, and the planet is behind the star, and you subtract it, you're left with just the light from the planet. So we were able to detect the light from the planet, and because the infrared light is proportional to the amount of the temperature, we were able to get the temperature of the planets, orbiting these other stars. So that was an incredible success for Spitzer. And part of it was that we were able to get a sense of how warm those planets were, how warm they were based on which part of the orbit they were in, because obviously if you're over here and there's sunlight is illuminating one side of the planet, that's warmer, but when it comes over here, you're seeing the night side of the planet. And so we could compare the day side temperature to the night side temperature of planets. And we were looking at these are called like Jupiter-like planets, or hot Jupiters. And so they tended to be like Jupiter, except much closer to their star. And we found there were planets that had relatively little day time and nighttime temperature differences, not as much as we would expect. What that meant is that these were planets that had must have fast winds to redistribute that heat across the planet. So just by being able to measure the temperatures of these planets along their orbit. And I think this was one of the most exciting results to come from Spitzer. And it's not even an area that I work in really. I work in it a little bit. Was the ability to tell that not only could we see the daytime temperature and the nighttime temperature of the planet, but the fact that the difference between the two tells us how much of a difference, how much of the atmosphere plays a role in redistributing the daytime temperature to the nighttime temperature. So essentially we could tell that there were winds on these planets. So those are incredibly exciting things. And I, again, highly recommend your viewers to go and check out some of these results, because they were certainly exciting for us, and some of them are incredibly surprising. But that's one of the great advantages of having these kinds of general observatories, and this is why they were called the great observatories. They're more sort of focused observatories. But yeah, to be able to do different kinds of science, and from the new ring around Saturn that we didn't know about, to planets around other stars, to the youngest galaxies which don't have stars that seem to be pretty old already, were some of, I think, really great hits of the Spitzer Space Telescope.
Yeah, you sent me a link. I'll throw it in the description to a website, to the Spitzer website. We'll learn more about the mission. 17-year mission. A lot of the pictures coming from it. A lot of the stuff you discussed. It sounds like the discovery of the planets would be, Spitzer's Freebird. But
pretty much, yeah. I like I said, even though I've expanded into that area now to study those, but really, I freely, because it's not my area, I have no problem touting that one and doing that hit over and over again, because it truly was amazing. And there's a lot of observations that we did of exoplanets, these planets around other stars, that is still, people are still studying. And that was what I was mentioning in terms of the Spitzer archives. It has huge archives over these nearly 17 years of the mission. And so scientists are still going through them. And sometimes they're re-examining things that have already been published with a new eye, so they can get a little bit more information out of it. Or there are things that are there that people still haven't found out yet. So that's so I have to be a little bit careful in saying that these are the only greatest hits. So the archive may yet surprise us.
Last thing I'll ask you about, because I'm not smart enough to be driven crazy by this, but if I was working for JPL, or had that level of intelligence, I think one thing that would drive me crazy, and you mentioned this in your answer, is the length of time it takes light to reach us and for us to make these observations. It reminds me a little bit of like finding a letter in a bottle on the beach that's dated 100 years ago or something. It is, and you have no way to know what happened in the 100 years from when you found that letter, whatever happened to the person who sent it. I just think because it takes so long, you're seeing these young galaxies, but as you said, they're not young anymore. It just takes so long for the light to reach us. I guess, or is it just one of those things where it's just a law of the universe, so I'd be frustrated by it? But I would think, I'd be staying up night after night thinking, what's happening, at that galaxy now? And I'll never be able to know. And even those galaxies that make it beyond our light cone as the universe expands, do you ever think about what you're seeing when the light reaches us versus what's happening contemporaneously? Or is it possible to think about those things without going insane?
Oh, absolutely, absolutely. No, this is the interesting thing about why astronomy is in many ways has analogies to anthropology, is that you tend to do population studies. Now, we live long enough to sort of follow, children as they become, teenagers, to become adults, and then to become older people, and so on. To get the arc, but more often than not, within one anthropologist's career, you can't wait for all of that to happen. So what you end up doing is you try and, if you're studying a particular population of kids, then you try and find a similar population that is older, and then another population that is older still, but is akin to that one. So that's what we end up doing in astronomy, is that we know that there are these very young galaxies that, we're seeing as they're, but then if you look a little bit closer, that means those are less further away, which means you're seeing them that they're less old. Now, it's hard to do a perfect apples to apples comparison, but you can say, okay, of what became of this group of children, well, let me see what is similar about them and then see if I can follow them at an older group and then an older group. So this kind of population study is how we get around that problem of, because yeah, it drives us crazy too. We want to know what happened to that thing, but we're doing the same things that most sociologists or anthropologists are doing, is you end up doing population studies. So you can't speak to that one child as to how they would have grown up. But what you can say is that children of, that were in this situation tend to have grown up to be like this, and then are adults that are like this. Again, not a perfect description, but I think if you do your controls right, if you're sort of narrowing your question well enough, you can make, again, reasonably or reasoned arguments and reasoned conclusions about what became of them. But yeah, otherwise, yeah, we'd go crazy, just like you're saying. It's like, what happened?
Well, what happened here is I had an absolutely great time speaking with you. Thank you so much for taking the time to join us on the Square and Compass podcast. I'll just mention everybody watching, hit the, all the things you say, hit the like button, subscribe button, follow, go give me money on Patreon if you want, all that good stuff. From your end of the world down at JPL, it seems like there's a ton of stuff happening with NASA, with JPL. If people want to learn more, I'll leave the link for Spitzer down in the description.
Mhm.
But I mean, if people want to learn more just about what's happening with JPL, what's happening with NASA, the Mars rover, all that type of stuff, where can they go, and where do they go?
So jpl.nasa.gov is the JPL website. NASA.gov is the overall NASA one, which encompasses all of the different aspects of NASA, which includes the human exploration, robotic exploration, which is what mostly we do at JPL, as well as the first A in NASA, the aeronautics part, which is, so you can go to all of those different kinds of things. And right now, as you said, there's a lot of exciting things going on. The Perseverance rover just landed on Mars not too long ago, so there's a lot of information about that. In terms of JPL's involvement in astrophysics, we are involved with the James Webb Space Telescope, which is the successor to both the Hubble and Spitzer Space Telescopes. In fact, it has more wavelength overlap with the Spitzer Space Telescope, and that will be launching, it's scheduled to launch October of this year, 2021. So we're all looking very forward to that. Then following that is the Euclid mission that you mentioned that Jason is working on. That'll launch a few years after James Webb. And so there's a lot happening. And but the one thing I will say is what you mentioned about whether you're, a question of intelligence. Intelligence is important for this, but the main thing that any science needs, not just space exploration science, is dedication. That's the one thing that I think outweighs everything else, is that it takes most of these things, they are complicated, they take a long time, but if people have the dedication, that stick-to-itiveness, as it were, is, I think, what has gotten us here with both the Perseverance rover, Spitzer mission, as well as the other missions that are coming up. It definitely, yes, intelligence is a valuable asset, but I've known very many intelligent people who just don't have the perseverance. And so they tend to not be very successful in whatever they're trying. So what I would say is don't underestimate, and don't just say you're not smart enough or whatever. It's like, yeah, smartness combined with the stick-to-itiveness, I think, is really what's given us a success. And I think that's, if there's a message to go out there, is if you love this and you're willing to put in the hard work and the time and the effort, then I think you'll be successful at it.